Okay. We don't really have much to do at all today. We are going to have a monitor. Someone from the SI office come and monitor me. They'll join in a little bit. We'll wait for them to join before we start. She didn't really have anything that would be we can make practice problems off of yet. She'll do that on Wednesday. So on Thursday's SI session, we'll have a lot of practice problems. Oh, there's Bella. All right, there's Bella. Okay, it's 5:06. I guess we'll go ahead and get started. So, like I said, we don't really have much to cover over today. But I'll go ahead and share the screen, and I made a Quizlet over what we learned on earlier today. It was mainly just vocabulary, so or it was entirely just vocabulary. So went ahead and made a Quizlet, and we're going to try out this little test function. If it doesn't work too well, we're just going to do the flashcards and do them that way. But I figured we'd try this out. So I have all the questions in here, and this should help you to better understand the vocabulary so that whenever she kind of gives you practice problems on Wednesday, you can kind of see how they work before you get to them. So we're going to start just with these written questions. So this is the definition, and you'll have to come up with the terms, and I'll type them in, and we'll see if they're correct. So the first question is subatomic particles, protons, and neutrons. Y'all remember the term that follows this definition? It's the very first thing she covered in the class today. I'll take that as a no. This was the I spelled it wrong on my notes. It's nucleons. There we go. I think that's how you spell it. But the nucleons, those are the subatomic particles, which are the protons and neutrons, and theoretically electrons too, but those aren't really as important as it pertains to radioactivity and nuclear chemistry. So whenever we talk about nucleons, we're just going to focus on protons and neutrons. All right, next one is the difference between the mass of an atom and the sum of the masses of its protons and neutrons. Does anyone remember the term that follows that definition? This one is going to be your mass defect. Yep, that's the difference in between the mass and the mass of the nucleus and the sum of the nucleons. And so we'll go into the next one. These two are just kind of general definitions. You don't really need to, memorize these two. This is just kind of some baseline information so that you know what we're talking about throughout the lesson. There's a few more like that too, but I'll point out the ones that need to know for the quizzes and the tests. So what determines the age of an, I kind of wrote the answer already in the question, but determines the age of an object based on the rate of decay of a particular radioactive nuclide. Since I already wrote it, I'll go ahead and give it to you. That's the half-life. So the half-life, remember how it works. So carbon-14 is radioactive because carbon-12 is the normal isotope for carbon. And so this has two extra neutrons. So it's radioactive. It wants to go back to carbon-12. But this requires 5,730 years for carbon-14 to lose half of its life. But remember, so if you doubled this to 1,000, what would that be? 1,460 years, it would be at a quarter of its original size, because you're taking the half-life, and then the second half-life, 1/2 times 1/2 is 1/4. So you're not getting rid of the whole thing. After 2 half-lives, you're only getting rid of 3/4 of it. And then it would go down to 1/8 and then a 16th. And so you'll never actually get rid of an entire substance through its radioactivity. All right, we'll go on to the next one. A larger element releases a positron, which causes the atomic number to decrease by 1 into a second smaller element. Okay, so this is one of the types of radiation. So if we look, I'll give you all the options. We have alpha emission, beta emission, positron emission, gamma radiation, and electron capture. So which one of those do you think fits into this? I'll give the options again. We have alpha emission, where it emits an alpha particle, beta emission, where it emits a beta particle, positron emission, where it emits a positron, gamma radiation, which it's a different kind of radiation, and electron capture, where it captures an electron. So which one do you think releases a positron? That one is going to be positron emission. Okay, so positron emission is where it releases a positron. And if you remember, a positron is a positive electron. You can kind of guess that from its name, just positive electron, kind of the roots of both words. But when this happens, when it emits a positron, the atomic number decreases by 1 into a smaller element. So it is similar to, is it beta emission? It's kind of the reverse of beta emission. And we'll get more into beta emission in just a second. So the sum of the number of neutrons and protons in an atomic nucleus. So break this down, the sum of the number of neutrons and protons in an atomic nucleus. What would that be? Any ideas? That is your mass number. So the mass number is the sum of the number of neutrons and protons in an atomic nucleus. And this is different from your atomic mass, because your atomic mass, the numbers that are below the elements on the periodic table, with all the decimal places that you use to calculate molar mass and all that stuff, those are the averages of all the isotopes' atomic mass. So let's take carbon. Yeah, let's take carbon for an example. So carbon has, I believe, 2 isotopes. It might have more, but 2 important ones, carbon-12 and carbon-14. So you have, and there's a lot more carbon-12 than there is carbon-14. So if you think about the atomic mass, the number on the periodic table, it's the average of the mass of carbon-12 and carbon-14. And you look at it, and there's a periodic table right next to me. The mass of carbon is 12.011. And so that means that there's a lot more carbon-12 atoms than there is carbon-14 atoms. But the mass number does not take into account the averages. It's just talking about the specific element you're talking about. So carbon-14, the mass number would be 14. Carbon-12, mass number would be 12. But carbon as a whole, the atomic mass is 12.011. Okay, so that's all of the fill in the answers fill in the blank answers. So move on to the matching questions. Let me move that. Okay. Okay. Okay, matching questions. So we have the terms gamma radiation, transuranium elements, types of radiation, that's supposed to be radiation, the half-life equation, and the atomic number, which is labeled as a Z. So looking at the definitions, we have the number of protons in the nucleus of an atom, alpha emission, beta emission, positron emission, gamma radiation, and electron capture. Elements with atomic numbers greater than 92, they're all man-made. And the half, or T, 1/2, that's supposed to be a subset, but Quizlet doesn't really like exponents or subponents. And then high energy electromagnetic radiation produced by an antimatter reaction. So let's kind of look at all these. What's one that we can mark right off the bat? 4, equation. Which one of these is an equation?
D.
D, yeah. So that's your half-life equation. The half-life, so T 1/2. Here, let me open up a Word document real quick. Or it's just a subscript, just like we do with all the elements, you know, H2O 2. That's what the 1/2 is supposed to be. So T 1/2 is equal to 0.693, which is the natural log of 2. You can just put 0.693 divided by K. And K is found out through the equilibrium constants, which we did way before. And she'll probably have some practice problems on Wednesday. So on Thursday's SI session, we can go into kind of solving some equations with the half-life equation. All right, so let's move on to number 5, the atomic number. Which one of these would be the definition for the atomic number?
A.
A. The number of protons in the nucleus of an atom. So yeah, that one's pretty straight, simple. The atomic number, it's how the periodic table is arranged, and it's the number of protons that are in the nucleus. It's not the number of neutrons, if you remember, because as you get further and further along the periodic table, the neutron amount will be different it'll be different from the proton count. All right, so now we have three different ones, and we have gamma radiation, transuranium elements, and types of radiation. So which go together?
I think number 2 is C, right? Wait.
Yeah.
Yeah.
That's right. C, elements with atomic numbers greater than 92 that are all man-made. So transuranium elements, I never remember covering this term specifically. So this is kind of another one of those general definitions. But if you look at the periodic table, after 92, which is uranium, they're all the man-made elements. And she kind of went over that more in lecture, going over each of the names, and kind of when you see the names, you can tell that where they were founded and stuff. That's kind of a thought to keep in the back of your head, that every element with an atomic number greater than 92 is man-made. And it continues being added on to this day. So the periodic table in here is at 111 is the maximum atomic number, but I believe the scientists have done it all the way up to either 118 or 119 atomic numbers. So, you know, a nucleus with 119 protons in it. And that would be, those are very short-living elements that are kind of useless for actual in-person use, but they're able to do it. So they name an element after wherever they did it. So now we have 1 and 3, gamma radiation and types of radiation.
I don't really know those. Is number 1 B?
Number 1, gamma radiation, that's E. That's
Oh.
the high energy electromagnetic radiation, which is produced by an antimatter reaction. And the only thing you really need to know about gamma radiation is that it's high energy. Because I believe last year, whenever I was taking this class, I believe she had a question that was, it was just simple. It was said, what is the type of radiation that has the most energy? And the answer was gamma radiation. Pretty sure I missed that one too. So It's very important to remember that gamma radiation is high energy. And when you think about it on the electromagnetic scale, the scale with visible light and infrared and ultraviolet and all that, gamma radiation is the highest, or gamma is the highest on the UV scale or EM scale. So it makes sense that it has the highest energy in terms of radiation as well. And then, so that just leaves B for the types of radiation, which is alpha emission, beta emission, positron emission, gamma radiation, and electron capture. And like I said, she'll go into all of these, especially on Wednesday, and she'll give some practice problems, and I'll have some more for Thursday's session as well. But we're just covering the definitions for today. All right, a larger element is broken down into the daughter element and an alpha particle is released. Helium with an atomic number of 2 and a mass number of 4. The starting element will lose 2 protons and the atomic mass will drop by 4. Which type of radiation is this? So if you look at it, it's releasing an alpha particle, which is that helium with 2 protons and 2 neutrons to make the mass number of 4. And if you remember the alpha particle, which one of these does it go with? Give me a guess.
Would it be alpha emission?
Yep. So it's pretty self-explanatory. When it releases an alpha particle, that just pairs directly with alpha emission. So, and the important thing to remember here is just that the alpha particle is a helium with 2 protons and 4 neutrons. And I do need to open up a Word document for that. Let me try. It's over here. There we go. Word. There we go. Okay, can you all see the Word document?
No.
Nope. Okay, let me reshare. There we go. Now you can see it?
Yes.
All right. So let me go ahead and make my font pretty big so you can kind of see. So the alpha particle is this, it starts with a helium. And on the left, oh, this might actually be difficult because Word doesn't really like to do this. Let me see if I can do that. Yeah, there we go. 2, and then 4. There we go. So that's kind of what it's going to look like whenever she puts it on a test. That is your alpha particle, a helium element with 2 protons and 4 neutrons, or atomic number of 4, not 4 neutrons. So it'd be 2 protons and 2 neutrons to get a mass number of 4. Because remember, the mass number is the sum of the protons and neutrons. So that's what it'll look like on a test. And I'll go ahead and do the other ones too. So the beta particle, that instead of an element name, you're just putting an E. And that E stands for electron. And there we go. So you start out with the E, and then for the subscript, it's just a negative sign, or you might see it with a -1. Either way, either of those two. She tends to use just the negative, so I'll keep it like that. Oh, no. It's not going to let me do it. Okay, it's not going to let me do it as a subscript. But then the superscript is going to be a 0, because an electron has negligible mass. It's like 1/2048 of the mass of a proton, so it's considered to have 0 mass. So the mass number of an electron is going to be 0, but the amount of protons, since an electron has a negative charge, you can consider the amount of protons to be -1. So that's what it's going to look like whenever you have an beta particle emission. It's going to be releasing this. Okay, So then we'll go on to the positron emission, and that is going to be, you're going to start out with the E again, but instead of a negative, since it's a positive electron, you're going to have a positive one as the amount of protons. Or she might just put it as a 1, she might just put it as a plus, but either way, it's going to have a +1 charge, and then the mass number is still going to be 0 because an electron still doesn't have any mass no matter what its charge is. So this is going to be positron emission. And then that is it, because gamma radiation doesn't work the same way as this. And electron capture, it's just an electron again, which is that. So that's all we needed there. Might go back to it, so I'll leave it up. Yeah, so the alpha particle, whenever it's talking about an alpha particle, which is that helium-24, it's always going to be this alpha emission. The energy required to decompose an atomic nucleus into its component protons and neutrons. Okay, so let's look at this a bit. So it's some type of energy. Well, that kind of just gives it away if you look at the answers, but required to decompose an atomic nucleus, so to break apart a nucleus into its component protons and neutrons. So you're splitting a nucleus into protons and neutrons, and a certain amount of energy required. I'm guessing you can kind of guess which answer it is.
We're still on the.
We're still on.
Oh, my
Word.
bad. You're right. I forget. Zoom is not my friend. There we go. Okay. So right here. Any guesses as to which one this might be?
Is it A?
Yeah. Nuclear binding energy. That's another general definition. You don't really get a quiz question over this, but it's always important to keep that vocab in your brain so you can just kind of know what she's talking about whenever she goes into more detail about all this. That's the way her class generally works, is she'll explain things in broad terms and then she explains the specifics of each thing she explained. So the nuclear binding energy is the energy required to decompose an atomic nucleus into its component protons and neutrons. Move on to 3. A smaller element releases an electron, which causes the atomic number to increase by 1. So you're releasing an electron, and the atomic number is increasing by 1. That part's more important for Wednesday, but a smaller element releases an electron. Which one would that be? We just talked about alpha emission, which is where it releases an alpha particle. So we know that can't be it.
Electron.
Yeah. Electron capture? No, that one is going to be when it captures an electron. So yeah, electron capture, I think we might have another question about that. Yeah, we have another question about that later. But electron capture is whenever the nucleus captures an electron, which then causes the atomic number to increase by 1, I believe. No, it decreases. But when it releases an electron, it's going to be beta emission. So beta emission is when it's releasing an electron. Alpha emission is when it's releasing an alpha particle. Positron emission is when it's releasing a positron. And electron capture is when it's capturing an electron. So number 4, it's determined by the ratio of protons to neutrons in the nucleus. Well, we already got nuclear binding energy. We know what that is, so it's not that. The atomic number, we already covered that. So we're between nuclear stability and nuclear transmutation. Anyone want to take a wild shot? This is going to be your nuclear stability. So The nuclear stability is going to be determined by the ratio of protons to neutrons in the nucleus. And that's the only thing you really need to know about nuclear stability. But if we kind of dig a little more into this, it makes sense because she already told us that every element that's above 84 is radioactive, right? Everything with an atomic number greater than 84, which is polonium, is going to be radioactive. Well, what happens whenever our atomic number starts increasing? The amount of neutrons per proton increases as well. So if you look at a periodic table, I don't really have one pulled up, but let's look at carbon. So carbon, the atomic number is 6, and so the number of protons is 6, and the number of neutrons is also 6 because the atomic mass is 12. So it's 6 to 6, which is a ratio of 1. But then if we go down to something, francium, 87 protons in it, right? Well, the atomic mass is 223. So that means that there's a lot more neutrons than there is protons. Because remember, the only thing that's adding to that atomic mass is protons and neutrons. And 87, if there was 87 neutrons, then the atomic mass would be 174, and it's 223. So we know that there's a lot more neutrons, which means that the ratio is going to be off. And if it's radioactive, that means it's going to be less stable. So you can kind of see as the number of neutrons increase related to the protons, which changes the ratio, it gets less stable. So that's where the term nuclear stability comes from. Let's move on to number 5, the powerful attractive force that binds protons and neutrons together in the nucleus. Again, this one kind of gives away the answer, but think about it in the nucleus. You need some type of force to hold all the protons and neutrons together. Because remember, they're not attracted by positive and negative charges, protons and neutrons, because neutrons are neutral. So what do you think? Which one of these is the powerful attractive force that binds protons and neutrons together?
Strong nuclear force.
Yeah. And that one, again, is just a general definition that she gave us. Just helpful to know so that whenever she gets more in detail, you know what she's talking about. So strong nuclear force is the powerful attractive force that binds protons and neutrons together in the nucleus. All right, now we got some true false questions. Because I set up flashcards to do this, so it doesn't really work. These are all going to be true, but we'll cover them together, or they should be true. Actually, they might not. I haven't looked over this. Oh, they're not. Oh, yeah, this is going to be a little awkward. But let's just go over them together. So we have atoms of the same element that have different number of neutrons. So what, do y'all remember the term that covers this? Because it's not mass number. These don't really go together at all. But atoms of the same element that have different number of neutrons. So it's the same element. Like, let's say you have 2 carbons. You have carbon 12 and carbon 14. What's the term that tells you what you're dealing with? Do you remember? The term is going to be isotopes. So atoms of the same element that have different numbers of neutrons are going to be isotopes of each other. So carbon 12 is an isotope of carbon, and carbon 14 is an isotope of carbon. And since they're the same element, but they have different number of neutrons. Okay, we'll go on to the next one. The conversion of one element into another. It's definitely not the energy that binds the nuclear binding energy. But what is the conversion of one element into another? Let's look at some of the other terms in case you don't have it off the top of your head. It was a big, long word. Any guesses as to what it might have been? Oh, did I get a chat? Oh, okay. Okay, so the conversion of one element into another, the term for that, which again, this is similar to man-made radiation. So she talked about it in lecture for just a second, but she said that people make gold. You y'all remember her talking about that? How you can make gold using chemistry?
Yes, a little bit.
Huh?
She kind of talked about it for like a split second.
Yeah, she just said it for a split second, but it was while she was covering nuclear transmutation. That's the conversion of one element into another. Again, that's just a broad term. She's probably not going to ask you on a quiz to give the definition of nuclear transmutation. But it is good to know that that's what it's called whenever you make something using chemistry or make a new element out of a separate element. But nuclear transmutation is the conversion of one element into another. Okay. Yeah, these really don't work at all. So this is an equation, right? The parent to the daughter. This is not how it's supposed to be set up. I'll just give you all the answer for this one because it's not really set up. But this is the nuclear equation. So this is how every radioactive nuclear equation will be set up, or something very similar to this. But the terms parent and daughter is just what they name the two elements. So let's say you start with uranium, and then you're going, let's say this is alpha emission. So you have the parent cell, which is, in this case, it's going to be uranium. It then becomes the daughter cell, which would be strontium, plus the alpha particle. And that's, so the daughter cell is what it becomes, and the parent cell is what it began as. And that's kind of the equation that's going to be used whenever she gives you all practice problems. And this will make a lot more sense on Thursday whenever we have actual practice problems to go over. But just know that the parent cell is what you start with, the parent element is what you start with, the daughter element is what you end with, and then the X just stands for either, or it stands for those things that we wrote on the Word document, the alpha particle, the electron, and the positron. It can be either of those. Okay, the inner electron is captured by the nucleus, raising the atomic number by 1. Is that positron emission? Let's look back at the terms that we had. So we're looking, so the question asks if it's positron emission. So let's look and see what the types we have. We have alpha emission, beta emission, positron emission, gamma radiation, and electron capture. So it's going to be one of these 5 types because these are the only 5 types of radiation that we cover. So we know what alpha emission is. That's when it releases an alpha particle. Look, releases an alpha particle. No, that's not what it's asking, right? So then we go back up. Beta emission. That's, do y'all remember what beta emission was? Beta emission is when it releases an electron. So if we're looking at this, an inner electron, okay, so we have electron is captured by the nucleus. So now it's not releasing an electron, it's being captured. Positron emission, let's go back up here. Positron emission, gamma radiation, which we don't have any questions over yet. That'll be a Wednesday thing. So we'll move that out. So we have positron emission and electron capture. If we go back down here, so it's either positron emission or electron capture. And it's saying an inner electron is captured by the nucleus. So do you think it's true or false?
False?
False, yeah. Because the positron emission is when it's releasing a positron. So that's a quick tip. If it says emission, I didn't know what that word was whenever I took this class the first time. So emission just means it's releasing. So if anything, you have alpha emission, beta emission, and positron emission, that means it's getting rid of it, sending it away. And so that's going to be releasing the positron. In this scenario, though, an inner electron is captured. So that's how you know it's going to be electron capture and not positron emission. All right, last question. The spontaneous emission of radiation by an unstable atomic nucleus, all elements with an atomic number greater than 84 are radioactive. This one doesn't really work for this either. Okay, so I'll just give you all the answer for this one too, because it's not really, doesn't really work like this. But this is the by the book definition of radioactivity. So when you think of radioactivity, you're thinking of the spontaneous emission of radiation. So an element that's giving off radiation spontaneously, which just means it's random and it's always happening, by an unstable atomic nucleus, because that means in order for it to be radioactive, that means the nucleus has to be unstable. That works for all numbers greater than 84. So anything past polonium, 84 through 118 or whatever the number was I said earlier. But that also means any unstable isotopes like carbon-14. Remember we were talking about with the half-life, and she was talking about during the class, carbon-14 is an unstable nucleus. And so that means it is considered radioactive as well. Before I click check answers, is there anything that was a little confusing that you kind of want to go over a little bit more? Also, real quick, these are going to be considered wrong, most of them, because I typed in very specific answers. Like with positron emission, I put in the beta particle as well. So if they're considered wrong, it'll say what the answer is, and we'll know if we got it right. But yeah, any more terms that you didn't really understand when she was talking about in class and you want to talk about again real quick, or you think you got all of them?
I'm good.
You're good? Anyone else?
I think I'm good too.
Awesome. All right, so let's check our answers and see. Oh, I knew I spelled that wrong. Okay, but yeah, nucleons, EA. I don't think she'll count off for spelling. But, oh shoot, I messed up here. I did not have that. Okay, I was confused by that. Okay, so radioisotopic dating, that's just the term used when you're talking about half-lives. So whenever you're dating, you know, she talked about woolly mammoths and all that, how they date those is using radioisotopic dating, and that uses the half-life. So those terms are kind of not synonymous, but they refer to the same thing. If you're talking about half-lives, you're talking about radioisotopic dating, and vice versa. Going down, positron emission, mass number, got all these. Good job, good job. Got that right. That right. All right. Well, we made a 90.
We're about to run out of time, Tanner.
Oh, yeah, we are. Okay, real quick, is there any more questions? No? Well, all right then. If y'all could put it in the chat real quick, your student ID numbers, so I can put that into EAB, then y'all are good to go.
Thank you.